My name is Pam Pearson. I'm the chair of Arctic 21 and also the director of ICCI. And we have a fairly full schedule, I would say, today, because what we're going to do is hear from Alexandra Jahn, who also presented back in August about her earlier paper. And then go ahead and do a bit of a debrief on COP29 and look ahead towards 2025. So as always, we're recording this session. Please let us know if you're uncomfortable with that. We're only going to record the two presentations and post those on YouTube. And as always, please go ahead and mute and turn off your video unless you're asking a question. So with that said, Alexandra, please go ahead and take it away.
Yeah, thanks, Pam, and hi, everybody. This presentation is going to be about a paper that was just published last week in Nature Communications, and I wrote that jointly with my colleague Celine Jose from the University of Gothenburg in Sweden. And we looked at the first ice-free day in the Arctic, and the title of the paper was "The First Ice-Free Day in the Arctic Could Occur Before 2030." These are the current projections of the first ice-free months in the September mean based on the CMIP6 models. So this is based on the SMIP community paper in 2020. So first look at the CMIP6 models. And one of the conclusions there was that first ice-free conditions are likely over 66% probability to occur before mid-century under all the CMIP6 scenarios. And that kind of started me thinking about, okay, so if ice-free conditions are going to occur under all scenarios by the end of the century for sure, and likely before 2050, we really need to start thinking about when what is that going to look like when it occurs. And just as a note, so ice-free in these scientific studies for over a decade now has been defined as sea ice area equal or less to 1 million square kilometers remaining. So it's not completely ice-free, but 93% of the surface area of the Arctic Ocean basin would not have any more ice, and the remaining ice would be located where we currently have the thickest ice, where the ice is being transported dynamically by the winds and the ocean currents north of Greenland and the Canadian Arctic archipelago, where it will stick around for a little bit longer. Like I guess I said, thinking about what that would look like when the first ice-free conditions occur, it kind of became clear that the first time we will actually see ice-free conditions in the Arctic, not in models, but from satellites, will be in the daily satellite data. And here is just one example of one model simulation looking at the daily sea ice area minimum in the dark blue and the monthly minimum in the lighter blue. And we can see that the first ice-free day in the specific simulation occurs in 2030. The first ice-free monthly mean doesn't occur until 2051, so 21 years later. And there's actually 5 instances of ice-free days before, in this case, the first ice-free monthly mean occurs. There is then another occurrence kind of that we call consistently ice-free conditions. So that's when year after year, the monthly mean, which typically is September at the seasonal minimum, is below the 1 million square kilometers threshold. So that's when we can reliably expect the Arctic to be ice-free. But so that shows that the first ice-free day could occur much earlier than the first ice-free months. But this is, again, just one model simulation. And so in the earlier paper, the review of ice-free conditions, we looked at that just in one model and found that there was a big range of how much earlier the ice-free day could occur compared to the ice-free months. And so in this paper here, we wanted to look at that. Wanted to look at how soon the first ice-free day could occur and how much earlier than the first ice-free monthly mean that could occur based on all the available model simulations from the CMIP6. So all the models that actually have the daily output of sea ice concentration so that we can look at that. important to note is like the first ice-free day. It's important because that's the first time we're going to see ice-free conditions. And so that's what's going to make the news when it happens. It's also something that I think a lot of people will kind of interpret our current interpretations or our current projections of first ice-free conditions potentially as the first time we actually see that, rather than the scientific definition of ice-free conditions in the monthly mean, which is the part we don't often say when we say first ice-free conditions. And so we thought it was really important to be very clear that there's very different occurrences of ice-free condition. The first ice-free day, which is primarily a symbolic event. So the first time we will see this big transition from a white Arctic, even in the summertime, that's dominated by sea ice, even in the summer, to a blue Arctic in the summertime when the sea ice is reduced so much that the Arctic really looks blue for the first time, versus the first ice-free monthly mean. And then really what has the biggest climatic impacts as well as economic impacts when we reach consistently ice-free conditions, when the Arctic reliably reaches ice-free conditions. So with that, so we looked at that in the CMIP6 models that had the daily output. So how could, and our main question was, how soon could we see ice-free conditions compared to present day equivalent simulations? So how did we do that? We looked for the occurrence of the first ice-free day, and then we looked backwards to the last time that the daily sea ice area minimum was at or above the 3.3 million square kilometers, which was the daily sea ice area minimum in 2023. So we did this work in the spring and summer of 2023. So at the time, that was the most recent sea ice area minimum. Since then, we've obviously had the 2024 sea ice area minimum in September of this year, which was above the 2023 sea ice area minimum, which means basically the count is still, we're still, everything is moved 1 year forward, because basically we're looking at how many years will it take from when we leave present day conditions, where we've kind of been bouncing around this mean state until the first ice-free Arctic, to look at what's physically possible. By starting all the model projections with kind of present day conditions, rather than looking at the actual evolution based on the model time. This also helps to remove some of the mean state biases that we know exist in Arctic sea ice simulations in CMIP6, because all the models, all the projections are calibrated to this present day state, no matter when that occurs in the models. So applying that to the CMIP6 models, we overall looked at 366 model simulations across 11 models for most scenarios, fewer for the lowest emission scenario because there weren't as many. And obviously there was a lot of internal variability in when the first ice-free day occurs. We already know that from the first ice-free months, that there is an internal variability uncertainty of over 2 decades, in some cases spanning up to 4 decades. And so we see similar things here. So we addressed that by looking at the earliest ice-free day, so the earliest ensemble member from a model that goes ice-free, and then the latest ice-free day from an ensemble. What's notably is that the first ice-free day could occur anywhere between 3 years, which is the quickest transition included here, but it could also take 50 years, or it could not reach ice-free conditions at all under the lower emission scenarios. So over 70 years here means past 2100, so when these simulations end, or even longer delay for the lower emission scenarios. However, for the earliest ice-free day, there's no strong scenario dependence on the earliest ice-free day. We can see that the fastest transitions to ice-free conditions occur under SSP 126, one of the low emission scenarios that keeps warming below 2 degrees Celsius by the end of the century, as well as under SSP 245 and SSP 370. And so the quickest transitions can occur under all the emission scenarios. Also looking at 7 to 10 years, which would still be relatively quick, again, under all scenarios except the very lowest, the SSP 119, which keeps warming at or around 1.5 degrees globally in the long-term mean. But the only scenario impact is really on the potential to avoid ice-free conditions at all, which only really occurs under the low emission scenarios. In terms of how much earlier the first ice-free day occurs than monthly ice-free in that same ensemble member, again, looking at the earliest and the latest, we can see that the first ice-free months can occur anywhere between 0 years and 30 years for the earliest ice-free day, but really occurs primarily within 6 years for the latest ice-free day, which again shows us that if we have an early ice-free day due to internal variability, there could be quite some delay for when the first monthly mean goes ice-free, whereas for the latest ice-free day, where internal variability delays the occurrence of the first ice-free day, the monthly mean follows soon after. Generally, the delay for the majority of the simulations is less than 6 years. So coming back to the overview of how many years the first ice-free day takes, we were quite surprised that we saw model simulations that actually transitioned to first ice-free days within 6 years or less compared to present-day conditions. Since again, that's like 3.3 million square kilometers. So that would mean we would lose 2.39 million square kilometers to get to that 1 million square kilometers threshold within that period. And so then we took a storyline approach to look at those simulations to understand how these this very rapid sea ice loss could occur to get to an early ice-free day. It doesn't mean that we think that's the most likely scenario. Obviously, based on the whole 366 simulations, we have 9 simulations that transition to first ice-free day in 6 years or less. It's a very low probability event, but it's comparable to 1,000-year flood events, which are unlikely, but they happen. We had one in Boulder here in 2013 with the Boulder flood, and we've seen these rare events happening around the world. So it doesn't mean it's impossible. It just means it's not the most likely scenario, but we only will have one realization of reality, and so it doesn't really matter what's the most likely one. We're just going to see one of these possible outcomes. So we looked at how these simulations transition to an ice-free day. As I said, the quickest transition was in 3 years, and we had transitions in 3, 4, 5, and 6 years in 4 different CMUP6 models for a total of 9 simulations. So here I'm just going to show you one example of how that looked like, because it actually looked very similar in all of them. All 9 figures are in the paper. And so in all of them, what they had in common is that they had this very rapid transition from 2023 equivalent conditions or present day equivalent sea ice area conditions to the first ice-free day over these 3 to 6 years, in this case, in 4 years. And the other thing that they all had in common was that the first ice-free day was an isolated occurrence with a rebound in the daily sea ice area minimum afterwards. This is an extreme case where it goes back to almost 3 million square kilometers, comparable to basically what we saw in 2012. Some of the other ones have smaller rebounds, but they all have that rebound before they reach ice-free days again in the future. So then we wanted to know how does this very rapid sea ice loss actually happen? What's the driving force for that? And we looked at a bunch of variables from these model simulations, both daily and monthly, because not all variables are available daily. For example, the sea ice mass. And what we found that all of these very quick transition simulations had in common is that they had very warm daily surface air temperatures in the fall, in the late summer and fall of the year. So the black line showing the pre-2023 mean temperature, and then the transition years for this one model simulation. Here again in the paper we showed for all of them, but here just looking at one model simulation so that it's easier to see. And so again, very warm temperatures. It was oftentimes the temperatures in the fall taking a long time to drop below the minus 20 degrees Celsius threshold that's considered to be representative of kind of winter conditions in the Arctic. Which delays the freeze up of the sea ice in the Arctic, And then also very warm winter conditions with conditions often above the -20 degrees Celsius winter threshold in the Arctic. So spring conditions during the depths of the winter in the Arctic. And that leads to the ice getting much, much thinner, which is what we can see here. Not all the models wrote out sea ice thickness. So we looked at total sea ice mass. So that includes both sea ice area contribution and the thickness contribution. But when we looked at the CS area, most models did not have a very big decrease in the wintertime area, just a small one. So it's really the sea ice thickness that decreases this total sea ice mass in the wintertime very strongly. And so that means that the ice is getting much, much thinner, which makes it much easier to melt. These very warm conditions occur because, depending on the individual ensemble members, due to a high prevalence of winter and spring blocking events that kind of lead to Arctic heat waves, as we see here, and as well as in some ensemble members, warm air intrusions, which again bring a lot of warm air to the Arctic, leading to these very warm temperatures. Which also shows that there's more than one possible path to losing so much ice over a short period of time. And then the other thing that we see during the spring and early summer is, and leading up to the first ice-free day, is that in many of these simulations, we see higher storm activity in the Arctic, which helps to break up the ice and make it easier to melt. So to summarize, CMAP6 models with daily output show that the first ice-free day could be reached within 3 to 6 years from present-day equivalent sea ice area state, but it could take also 50 years or even longer because internal variability will really determine when the first ice-free day occurs. And since that really comes down to the specific sequence of weather events in the Arctic, we have no way of predicting that right now, but it shows that it could happen relatively quickly. The weather events that lead to these rapid transitions to ice-free days in 3 to 6 years are characterized by very warm fall, winters, and in some cases springs. And these are made possible by winter and spring blocking events and or warm air intrusions, depending on the different ensemble member. And all of these events are projected to increase in frequency in a warmer world. And in fact, we've already started to see heat waves like that in the Arctic during the winter time. The first ice-free day could precede the first ice-free months by several decades, or they could occur in the same year. Again, this is down to internal variability that will determine the offset between the first ice-free day and the first ice-free months. And in most cases, ice-free conditions are delayed by less than 6 years compared to the first ice-free day. The only possibility to potentially avoid ice-free days in the Arctic, as well as earlier studies showing also potentially preventing ice-free months, is to limit global warming to 1.5 degrees above pre-industrial in the long-term mean. However, it's really important to note that even if we reach ice-free days, which again are primarily a symbolic event, showing the impact of human-caused climate change on the natural environment by transforming the Arctic from a white Arctic Ocean to a blue Arctic Ocean in the summertime, any reductions in future emissions will reduce the length of the ice-free season in the future. So even if we can't avoid first ice-free days, emission reductions will have a big impact in how the Arctic looks like at the end or even in the second part of the 21st century. So with that, I'd be happy to take any questions.
Thank you so much, Alex. And if people could either just turn on their videos or raise their hands, or if you happen to be on a phone, simply speak up if you have any questions. I'm going to ask a first couple. One is to ask you to go back to that example slide, which you said was showing one of the models with an ice-free day. I think it's forward a bit more.
Or do you mean this one? Or
Another one, I think. No, sorry. Keep on going forward, not backwards. Keep going.
oh, okay, forward. Sorry. Yeah.
Yeah, forwards in your presentation. This was
This one?
yes,
Or
that
this?
one. Thank you. Sorry, go back. Great. Um,
Sorry,
uh,
I keep this one, right?
yes,
Yeah,
exactly.
there's some delay, so I'm sorry.
No worries. One quick question, a more technical one. When you're saying, 1.5 lower Paris limit, I assume what you're meaning are the SSP1 scenarios where you actually have a peak of 1.6, but then it goes down quickly.
Yeah,
Okay,
I mean, it depends on the individual model, like where exactly they peak,
exactly.
depending on their sensitivity to the CO2 forcing, since what's
Mhm.
prescribed is the greenhouse gas emissions, and then the models decide how warm they get.
Yeah.
It's just like we looked at the quick transition simulation specifically at the warming, and all of the early ice-free days happen at a global warming level of 1.5 degrees or above.
Okay. Yeah. And then for this particular slide, I was interested because you said most of them showed this same pattern. And what was striking here is that you actually, it looked like you had before the first ice-free day, actually 3 years of record lows. Is that the case for all of them, or am I misreading the slide?
So that it's like, so the transition to the first ice-free day doesn't happen from one year to the other. So in the fastest one, we have a transition in 3 years. So we have two record lows, and then the ice-free day. This one is 4 years.
Mhm.
And like we look, yeah. So we do have several years of record. I mean, this one is kind of like 2012. So we have like two new records basically before we hit the ice-free Arctic.
Okay. And that was kind of general across the different models
Yeah,
then.
yeah, that they kind of had like somewhat not even, but kind of even. Some of them had like a 1 year plateau in the middle, where 2 years in a row were somewhat similar before they dropped again. That was for the like 6 year long ones. That took a little longer than the 3 year ones, but yeah. So
Yeah, but in any case, kind of similar to the state changes we saw in 2007 and 2012.
exactly, yeah, and in fact, like that's kind of how we could get to an ice-free Arctic. So it's just kind of above, like basically it was three times the 2011 to 2012 sea ice area drop that we've seen. We would be at an ice-free Arctic, and it's actually less than three times. It's like more like 2.4 times or something that. And so yeah, these actually qualify as like rapid ice loss events. If you've heard of those, there've been some papers on those. So we see those in a lot of CMUP6 models. And while we haven't observed a rapid ice loss event, if the 2012 minimum had actually occurred within a 5 year period of the 2007 minimum, that would have been a rapid ice loss event. It's just based on how that's defined, like it has to occur within a 4 year period. And so
Yeah.
it seems like it's definitely possible based on the kind of drops that we've seen in the past for the record minimums, to kind of get these kind of reductions year over year in sea ice area.
Okay. And final question, when you were looking at the similarities, it looked as though all of the models basically had the Arctic skimming over in a way in winter. Um,
Had the
is
Arctic
that the
skimming over?
case?
Sorry.
Yeah, in other words, sorry, that's probably an American ice term. In other words, you ended up having ice formation across the Arctic uh, even towards, well, or were these only going a few years out into those ice-free years? Because in other words, you weren't seeing ice-free springs or falls in any of these runs, but was that because temperatures were below 2 degrees?
So the ice-free days, they all occurred between mid to late August and early September.
Mhm.
And but in other simulations that I looked at towards the in the second half of the 21st century, depending on the emission scenario, we can see up to under the SSP 585, we can see up to over 6 months of ice-free conditions potentially, starting not in the spring, but starting in the summertime and going all the way to January, basically. So that's in the monthly mean. So that's under the highest emission scenario, but that's so that's in the later part of the 21st century where we could get ice-free conditions, and in order to get ice-free conditions in the spring and winter time, we need really high CO2 levels. I looked at that about a decade ago. Like we need in these long extension simulations. It occurs somewhere in the 23rd century under the extension of the SSP 585, like over 1,400, I think, CO2 level or something, but that would be needed to make the Arctic warm enough in the wintertime to prevent the formation of sea ice. So that, luckily, is still quite some time off that we don't get any sea ice formation in the Arctic, since it still gets really dark and it gets dark, and hence it gets really cold in the wintertime.
Exactly. Yeah. Mike, please go ahead. Sorry to make you wait.
Where in the Arctic was the ice sort of holding on the longest until it sort of gave up and dropped to ice free?
Yeah, we didn't look at that specifically in this study, but I looked at that in the CMUP6 models in the monthly mean, and basically that's where this figure comes from. So it's limited to what's also been termed the last sea ice refuge area, which includes some of the marine protected areas in north of Nunavut and other in the Canadian Arctic archipelago in general. And that's where the sea ice kind of will stick around the longest. We looked at that too. That doesn't mean it sticks around forever, but if warming is limited to less than 2 degrees, that we can actually avoid losing the last million square kilometers, and so some sea ice can remain throughout the summer. So we will retain a small percentage of multi-year sea ice. For warming above 2 degrees, that last sea ice melts too, and it takes, depending on how strong the forcing is, anywhere between 7 years to 40 years to melt that remaining 1 million square kilometers.
Thanks.
Yep, thanks.
Other questions? Yeah, Melinda, you just rejoined, or did you have a question?
I just got bumped off.
Okay.
Okay.
Okay, if there are no other questions right now, Alex is going to remain for the COP29 and sort of subsequent discussion. So feel free to pose questions to her.